Welcome back, everyone. Good to see you all again in person and in Zoom. I missed you guys a lot last week. You know, we had the inclement weather coming into town. Fortunately, I think it wasn't as bad as it could have been, but Tuesday night, I'm just sitting in my office at home and I'm like itching to give a Business Analytics 6354 lecture. So I have a lot of pin-up database energy to get out tonight. Anyway, welcome to either Business Analytics 6354 or MIS 7373, whichever you like. So on tonight's agenda, a couple of administrative things we're going to cover, and then we are going to be covering all of the content that we normally would have covered last week. And fortunately, we have a little bit of kind of flex time built into the schedule where I can shift some things around, and we're going to wind up covering all the same stuff that we would have anyway, so we're going to wind up being totally in good shape. But you might have noticed, or maybe you didn't, but I promise if you go check, there is an updated version of the syllabus, version 2021.9.14, because it's versioned by the date, that is updated to show that class was canceled last week due to inclement weather. And basically what's happening here is all of our content for September 14th is moved to the 21st, which is today, and then the content regularly scheduled for the 21st is moved to the 28th, including our second exam readiness quiz. So we're not going to be doing that tonight. And then we're just kind of combining that with the content that would have normally been covered on September 28th. And there's enough room in there that I think we'll be able to cover all of that next week without a problem. Now, of course, if we aren't able to cover all of this in the allotted time, whatever we don't cover, we'll just shift to the second half of the semester. And of course, anything that we don't actually cover in class wouldn't be on exam 1, which is coming up in 2 weeks from tonight, where we get to demonstrate all the excellent stuff that we have learned so far. It's going to be exciting. Looking forward to seeing you guys dominate exam 1. Second half of the semester is just exactly the same. That's when we start getting more into our structured query language and our normalization, kind of the more technical aspects of the class. So I'm looking forward to that. I imagine you guys are looking forward to that. I hope you're looking forward to that. Any questions, comments, concerns about these logistics, or are we feeling good? Feeling good? I'm feeling good. Awesome. So earlier today, assignment 2 was posted. This is kind of similar to the Bearcat problem we worked in class, where we have it's about a page-long story about the a database system that the NCAA, the college sports people, might use to track basketball players and basketball teams and basketball games and referees and things like that. So there's a big story. You're going to identify your entities, attributes, relationships, your cardinality and participation, your structural constraints, the whole thing. Create an ERD. Might have some semantic integrity constraints that we also have to list out. Okay, but it's kind of the same idea as we did with Bearcat, where you read the story and create the ERD. Now, in the past, I have done this as an individual assignment, and I kind of got the feeling going through these submissions that, you know, some people were really getting it, and then some people really weren't, right? And they were either resorting to like finding a solution on the internet or something like that, which isn't a good learning experience for them, or they were turning in complete garbage, which isn't a good experience for them either. So that's why I've kind of taken this, I've had a teaching philosophy change in the past couple of years, in that I actually like for people to work together on these big complex assignments if that helps your learning style, right? Because instead of just going, oh my gosh, I have no idea what I'm doing here, if you work with someone, you can kind of teach each other and build off of each other and help one another, and I'm totally fine with that. So I'm good with you guys collaborating, or you can be individual, whatever you want to do. It is a little bit lengthy, so I wouldn't put this off too terribly long. And if you do work in a group, just put the names of the people in the group, and when you think group, think maybe 2 or 3 people or something. I don't want one group of 29 submitting, right? It would make grading a lot easier, I guess. But, right? But yeah, I think 2 or 3 people, something like that. And only one of you should submit it to Blackboard, but you should just put in big bold letters at the top who all contributed to the assignment. So that was posted a couple hours ago. Take a look at that. If you have questions, send me an email and let me know. So speaking of modeling, which is what we're doing in assignment 2, what we've been talking about a lot so far, you guys have come a long, long way. On our very first night of class, we introduced this very basic model of Dave's Dog Wash, where customers own dogs and employees groom dogs and employees work at locations and so forth and so on. Very basic entities and relationships. And then last week or 2 weeks ago in class, in our last class meeting, you guys did this, which is a heck of a lot bigger and more impressive than this, right? We read the Bearcat story. We decomposed it into, what was it, 5 smaller stories? And then we put those stories together to create this big, impressive entity relationship diagram that captures all of the business needs and the use cases for Bearcat Incorporated, right? And we have these special symbols that represent if attributes are optional or required or derived, and which ones are our unique identifiers or our primary keys. We have notation here describing whether entities are required to participate in the relationship or whether their participation is optional. And if they participate, the maximum number of times they can participate, be it just one time or many times. We have this notation here that represents if this entity participates in only one relationship, both relationships, or either just one or both, which is what the straight across arc notation is here. We have our weak entities and our identifying relationships. Oh, actually, this isn't what we drew. We're going to draw this a little bit later in class tonight. This piece right here. So we've done a lot of good learning here. We have our deletion constraints on here. So being able to understand and describe what each one of these symbols means is something that hopefully we're starting to feel kind of comfortable with and that we could do on an exam. And being able to do that demonstrates a real understanding of our entity relationship grammar and just kind of this general idea of data modeling and database design. And we're just going to keep getting better and better and better at this. Good job, guys. Good job. So with that, I want to move into this week's content where we're going to expand and make this a little bit more precise and a little bit more ready to create our data definition language code that we're going to use to actually implement a database like this in something like Oracle or MySQL or whatever DBMS, relational DBMS we're using. So in module 3.2.4, we're going to do our decomposed design-specific entity relationship diagram. And in this module, we're going to address these 2 really weird things, these things that might shake you up a little bit on the inside. First being that multi-value attributes, as we have modeled, oh, actually it's disappeared from here because I have the wrong symbols there. Multi-value attributes, as we've discussed them previously, don't really exist. It's not a thing that we can do in relational databases. And many-to-many relationships, and we've kind of foreshadowed this a little bit because we said many-to-many relationships are really just 2 one-to-many relationships coming together, aren't really something that we can create in our database. So we're going to look at how we address these 2 issues tonight. So as I mentioned, multi-value attributes aren't really a thing in your database. This is only a conceptual modeling concept, right? And so ultimately, what we're going to wind up doing is taking our multi-value attribute and creating either a one-to-many or many-to-many relationship with another entity. And in this case, we'll see it's a weak entity in order to get all of these multiple values that would be associated with this attribute. And then similarly, many-to-many relationships don't really exist. They're just this combination of 2 one-to-many relationships. So how we actually need to model a multi-value attribute in order to be able to create it in the database. So building on the examples that are in the book, this is how we're currently, if you've been thinking about what this data would look like, this is currently how we're kind of envisioning the values of this multi-value attribute building, right? Where we have a plant number that has, or a plant that has a plant number, a plant name, a budget, and then some number of buildings. And in this case, maybe we put all these multiple values into this one cell, or maybe we split them across multiple rows, right? But in this case, in this kind of visualization of what we're trying to do here, we have some rows here that don't have values, and it's particularly troubling that we have some rows that don't have values for this primary key, this unique identifier, which is required, right? We're required to have values here, and yet we don't. So one way we could, of course, fix this would be just to repeat these values, right? Plant number 10, Underwood, budget of 3 million for both building 1, building 2, and building 3, right? We just repeat this. But we've introduced two new problems here. One, now just the plant number by itself is no longer a unique identifier, as we've previously been thinking about it. We have to now combine plant number and building together to uniquely identify each row in this table. But then also, now we have this repetition, right? For plant 10, we say the plant name is Underwood. And for plant 10, it's Underwood. And for plant 10, it's Underwood. Right? We're just saying the same thing over and over again without adding any new meaning or any new understanding to the data, right? And repetition that does not meaningfully add anything to our understanding of what's going on is called redundancy, right? This is redundant data. So imagine we wanted to change the budget of this Underwood plant from $3 million to $10 million. We're changing the budget for one plant, but yet we're going to have to update this value in 3 different places, right? So this redundancy makes this inefficient. And also, what if something weird happens while we're updating the budget, and we update the budget for this row and for this row, but not for this row? And now we don't know, is the budget for the Underwood plant 3 million or 10 million, right? We get back into the same problem that we had with our 2-schema architecture, in that we have a data integrity problem. So we introduce all kinds of issues if we start creating designs that allow for redundant data, right? So this is not a great way to fix this. Instead, what we're going to do is replace this multi-value attribute with a one-to-many relationship with another entity that is going to contain all of the buildings that are associated with each plant. Okay, so now we have a plant houses a minimum of 1 and a maximum of many buildings, and a building is housed by or associated by, whatever you want to call this relationship, a minimum of 1 and a maximum of 1, or exactly 1 plant, right? So now we say plant number 10, Underwood, that has a budget of 3 million, has building 1. Plant 10 has building 2. Plant 10 has building 3, right? So we're capturing these multiple values for building for each plant, now without introducing any data redundancy, right? If we want to update the budget of this plant, we only have to update it in one place. And since there's only one place to update it, it would be impossible for any kind of data integrity issue to seep in here, right? We can't get this value out of sync because it's only stored in one place. So that's kind of our next step of making our model more precise, is to take these multi-value attributes and model them such that we are keeping these values in another entity. And in this case, we've modeled it as a weak entity. And again, this is also kind of just a conceptual modeling construct, this idea of weak entities and identifying relationships, because when we actually create this table in the database, it's going to be as much a table as any other table, right? We just establish this relationship between the building table and the plant table, and we'll be seeing how we technically do that as we move through the rest of the material. So a little bit more complexity here, but solves our data redundancy problems. Oh, and in this case, so now that we have this new entity that has these values of plant number and building ID, plant number is what we call a foreign key, and we're going to learn more about what exactly a foreign key is a little bit later tonight. This is a foreign key that refers to this candidate key, and in this case, a primary key in the plant relation. So this foreign key establishes the relationship between these two entities. Building is a partial key, and note that we have indicated that by putting a dotted underline underneath the name of the attribute there. And then together, these two attributes make up a composite primary key that you can uniquely identify every instance of a building. Okay? So if I said, which one of these rows represents building 2 at plant 11, it's this one, right? There's one and only one value for that. Building 3 at plant 10, it's this one, right? Building by itself is not a unique identifier. If I said point to building 2, well, I don't know if you mean this one, or this one. But plant 13 building 2 is this one, right? You got to have both of these things to uniquely identify an instance in this entity. Now, I said this is a little bit more complex, but eliminates the issues of data redundancies. And this is going to be correct for the majority of transactional databases, right? If you are creating a database to be actively used by your business, 9 times out of 10, 95 times out of 100, this is what you're going to want to do. This is called a normalized database, okay? But there are some situations where if we're doing data mining or data warehouses, or if we have data lakes or something like that, where we are perhaps archiving data that's not going to be changing, we may actually want to reduce the computational complexity and accept the burden of dealing with this redundant data in the name of performance, right? Because to do this normalized design, now every time we want to see data about the buildings for a particular plant, we have to read the data out of this table, we have to read the data out of this table, and we have to do this computational comparison of the primary key and the foreign key to join them together, okay? I mean, this takes like a millisecond, like very, very small amounts of times, but if you're talking about, tens of billions of records in each one of these, that can be, a pretty big overhead, right? So there may be some cases where you want to store this data in its unnormalized format. You're going to be using more storage space, and your data is not going to be as easy to manipulate. But if you're only reading, if you're only doing like data mining type stuff, this might actually be the better way to go, okay? But for most business applications, normalized data is what is going to be the best approach. Yeah. Oh, and what you choose depends on the business's needs. It's the answer to almost everything in this class. What's right, what's wrong, depends on what you're trying to do. Let's see, what are we looking at here? Oh, our second thing. I was like, what's happening? What's happening? Here's my red highlighting. You may not be able to see this on the camera, but there are 2 relationships here that we're highlighting in red, which are our many-to-many relationships. That's the second thing in this ERD that we're going to be fixing. So right here is where we've gotten rid of our multi-value attribute and created a new entity to store the multiple values of building for each plant. Now we're going to decompose one of these one-to-many relationships, where an employee can be assigned to many projects, and a project has assigned to it many employees, and a dependent can participate in many hobbies, and a hobby can have participating in it many dependents. All right, so let's do the dependent-hobby relationship. And note that just for the simplicity of saving some room on the screen, I have not included all of the attributes for dependents and hobbies. I've kind of toned it down a little bit, and I've just made up a couple of data points here. So we have Mark, Jill, Norm, Mike, and Sue. They all have a birthday. They all have a gender. Then we have these hobbies: softball, flag football, knitting, cycling, movies. They're either indoor or outdoor activities, which is notated by either an O or an I. And they're either group or individual activities, which is notated by either a G or an I. So if we want to represent what hobbies a particular dependent is engaging in and what dependence a hobby has engaging in it, right, in both directions, one thing we might consider doing is just kind of mashing all this together, right? So, you know, this row here represents Mark playing softball, which is an outdoor group activity. This row is Mark, who has this birthday and this gender, doing flag football, which is an outdoor group activity. This row represents Mark doing cycling. This row is Jill doing knitting. This row is Jill doing movies, and so forth and so on. But what is the problem we have introduced here? Yeah, name is repeating again. Birthday is repeating over and over again. Gender is repeating over and over again. Like, what if we decide we want to start playing flag football inside, like inside the gymnasium instead of outside? We're going to have to update this record, and we're going to have to update this record, right? Or if we started watching movies outside, we've got to update this and this. We've got to do multiple updates because all of this data is redundant. All of this data is redundant. If you need to update someone's birthday for some reason, maybe there's a typo. This should be 1954 instead of 1945. We would have to update this in multiple places. So yeah, we've introduced some data redundancy here. Lots of redundant data. So what we can do to be better is to decompose this many-to-many relationship into two one-to-many relationships using a special type of entity called a gerund. Okay, so in the gerund, we're going to take the primary key of each of the tables in this one-to-many relationship and put those values in this table. And so now name, our primary key from dependent, is going to be a foreign key that links this participation gerund to the dependence table. And hobby name is going to be a foreign key that links this participation table to our hobby table, okay? And so kind of ignore for a moment the fact that we're repeating our names over and over again. This actually isn't redundant, even though there is some repetition, because this is just the unique identifier for each one of our dependents, okay? But this row in this gerund represents Mark, who has this birthday and this gender, playing softball, which is an outdoor group activity. This row represents Mark, who has this birthday and this gender, playing flag football, which is an outdoor group activity, right? And if we need to make a change to any of the data about one of our dependents, we can just change it here, right, in one place, and that kind of automatically changes it any time that we look at this relationship. There's only one place that we have to change it. Same for our hobby stuff. So we've gotten rid of our data redundancy now. So our gerunds are a product of decomposing these many-to-many relationships. We sometimes also call these a composite entity or a bridge entity because they bridge these two other entities. And much like our weak entity that we created when we were getting rid of that multi-value attribute, this is one of those things that is not a part of the business rule, right? This isn't something that your business person is ever going to describe to you, right? This gerund is an artifact of what we have to do to make it technically possible to get this type of relationship into our database, okay? So when you start putting things like this in your model, you're now getting to the point where it's a little bit less human intelligible by someone who hasn't taken a class in data modeling, for example, right? Your customer, your boss may look at this and go, well, what the heck is this thing? I said dependents participate in hobbies. Why do we have this stuff in the middle here? And now you can explain to them why. Well, we got to decompose a many-to-many relationship into two one-to-many relationships, and we do so using the gerund. That's what I would say. Mic drop. Yeah, so this is kind of what we were just saying here. So now we have decomposed this many-to-many relationship between dependence and hobbies by including this gerund. I don't really have room to squeeze this into the slide here, but on page 116 of your book, it goes through kind of this same process to decompose this. So I would encourage you to actually maybe try to do this on your own. Thoughts, questions, comments, concerns about that? All right. And notice in this one, we do have, and we talked about this a little bit already, this situation where we have an attribute of the relationship, okay? And so that's another thing that gerunds kind of help us out with. Because remember, we had this example where we had this relationship between dorm rooms and students, and we asked the question, well, is rent a property of the dorm room that all students are going to pay the same rent, no matter what the student's particular situation is? Or is rent an attribute of the student that the dorm room, or that the student is going to pay their individual amount of rent no matter what dorm room they're in? Or is this some hybrid situation? And I promised you that we would talk about how we're able to make an attribute a part of a relationship. And the gerund is the answer to this. So to illustrate that, we have an example here. We have vendors that import products. And these products have a cost, which in this case is a function of both the vendor that is importing the product and the product that is being imported. Okay, so imagine now that we have our vendor, we have our product, and we have our price. Okay, so we have a gerund decomposing this many-to-many relationship. We have these 3 vendors, Buffett, Gates, and Jobs. And we have these 5 products, soup, noodles, chocolate, nuts, and coffee. Notice that product has optional participation in this relationship. And sure enough, we do have some products that aren't participating in the relationship. But all vendors are required to import some product, and we do see that represented here in what is effectively an instance diagram. Okay? Now, each row in this imports table in our gerund is representing an individual vendor importing some individual product, and then here's the cost of that. So this first row is Buffett Incorporated, so B-U-F-F-E-T, importing product P11, which is soup. And Buffett soup cost $7. I don't know if that's per pint or per gallon, but it's $7. This next row, we have Gates, so V5, Gates Incorporated, importing product P11, which also is soup, for a cost of 10. So we have Gates, soup, which is 10. This row in our gerund is representing Gates importing product P17, which is chocolate. So we have Gates, chocolate, which costs, where are we, 17. So Gates chocolate is 17. This row represents Jobs Incorporated. So we have Jobs importing P17, which also is chocolate, for a price of 19. And then finally, Jobs Incorporated importing P23, which is coffee. Is this iCoffee and iChocolate? I don't know. For $13. So in the current state, with cost being an attribute of the relationship, we're saying the cost of this product depends both on what the product is and who is importing the product. But what would happen if we changed this, if we made cost an attribute of the product instead of the relationship? Okay, now we're saying all soup costs $7, all chocolate costs 17, all coffee costs 13, right? So now we're in a situation where Buffett soup is going to cost $7, and Gates soup is going to cost $7. Gates chocolate is going to cost $17. Jobs chocolate is going to cost $17. And Jobs coffee is going to cost $13. So we have two situations here where the cost of the product changed because we're saying the attribute cost is a part of the product, not a part of the relationship. Is this the way the world works? Maybe in some worlds it does. There's probably some products that the price is regulated in this way such that no matter who the vendor is, they have to sell it for a certain price, right? I don't know that soup, noodles, chocolate, nuts, and coffee fall into that. So maybe this is the right data model for some situations, probably not for this situation. Or if we made cost an attribute of the vendor, now we're going to say everything that Buffett sells is $7, everything Gates sells is $10, and everything that Jobs sells is $19. So now our Buffett soup is going to be, again, $7, and our Gates soup is going to be $10, and our Gates chocolate is going to be $10, because everything Gates sells now is $10. Our Jobs chocolate is going to be $19, because everything Jobs sells is $19, and our Jobs coffee is going to be $19, right? So now we've messed up the price of Jobs coffee and Gates chocolate. Is that all that's messed up there? I mean, if the person is selling multiple different types of products, they can sell different products for different prices, right? I can't even really think of a good example of when you even might have a plausible business case like this. Maybe there's one out there and this would be a good design, but I don't think this is a good design for this current model or this current business problem. So the point here is, like we had mentioned before, placement of attributes is important because it changes kind of what we're describing in our business case. And to get this, what seems like kind of the most reasonable model here, this cost attribute is just an attribute of our gerund. The gerund is what's allowing us to do this attribute as part of a relationship. It's good stuff. It's good stuff. I need some Gates chocolate, I think. Getting a little peckish up here. Cost depends on both the vendor and the product. Therefore, it remains an attribute of the imports gerund. And so this is kind of our higher level conceptual model. When we get to our decomposed design specific model, this is what this would look like. Right? So we have our vendor ID and our product ID as part of the imports gerund, as well as this cost attribute. So now, in this situation, what would we say the primary key of our vendor table is? We just have these two attributes here. Which one uniquely identifies? Actually, they could both uniquely identify, but we have a little special notation here indicating which one is the primary key. Vendor ID, right? We know because it's underlined there. In our product table, it is product ID. In the imports table, we have is just product ID? It's a composite, right? Because if I say which row is product ID P11, I don't know if it's this one or this one. If I say which row is vendor ID V5, I don't know if it's this one or this one. But if I say point to vendor V5 product P11, it's this one and only thing, right? This is a unique identifier for this imports table. So we have a composite key of vendor ID and product ID. And individually, vendor ID and product ID are foreign keys. Vendor ID is a foreign key that refers to vendor ID in the vendor table, and product ID in the imports table is a foreign key that refers to product ID in the product table. And we're going to have a more concrete definition of what a foreign key is real soon. I know we're saying some words, we're kind of introducing some terms without a lot of background at this point, but we will get there, I promise. All right. So we talked about multi-value attributes. What do we have to do to actually capture multi-value attributes in our database? What's that? Well, actually, we did the weak entity. So we had another entity that we linked to it, and we had a one-to-many relationship there. But the bridge entity or the gerund is what we did to decompose our many-to-many relationships.
Someone said vendor ID on the Zoom.
Mm-hmm.
Says vendor ID, I don't know what.
Oh, OK. Probably answering one of our, I think primary key of the vendors table. So spot on. Good job. Unless that's the answer to something else, and then maybe not a good job. But I think you did a good job. I have faith that you did a good job. All right, so moving on to module 3.3, we're going to talk about what happens when we do things wrong or how we might do things wrong. So we're going to talk about semantic modeling errors as well as syntactical modeling errors, and talk about kind of how these pop up and how we manage that. So we say that errors in our modeling can be related to syntax, which just simply means we're using the symbols incorrectly. We're using our ER modeling grammar wrong. Yeah? And these are relatively easy to spot, even if someone doesn't know, what we're trying to model, right? They can know nothing about the business case or the business problem that we're trying to solve. If they know how to use the ER modeling grammar, they're going to be able to identify that something's not right. Okay? Errors in syntax. Semantic errors, however, are instances where what we've modeled doesn't accurately capture what's in the business rules. And these can be kind of tricky. These can sneak up on you because it's not a right or wrong answer. We've talked about how there is some element of creativity in database design, and there's some room for interpretation of business rules and trying to create a technical solution that captures those. But it can be difficult to spot when we've done something that doesn't accurately capture what the business wants to do, because maybe we don't know exactly what the business needs to do, wants to do, or maybe we have a misunderstanding or we've just made a judgment call that someone else would make a different judgment call. So these are the ones where kind of your experience comes into play, and you kind of have to get a feel for things, right? So for example, should something be an entity, or which attributes should be together in an entity? Or is something an attribute versus a value of an attribute? And this is something that can be kind of confusing for kind of learning data modeling, right? For example, think about if you're at a restaurant, right, and you've got milk. Is milk an attribute, or is milk a value of some other attribute? I'd say it's probably a value, right? Like it's food item or something like that would be the attribute, and you would have values of food item that's like milk, soda, or maybe drink, right? Drink's the attribute. So what drink do you want with your meal, and possible values are soda, water, milk, orange juice, right? Okay, so milk would be a value in that case. But think about if this restaurant is a coffee shop, right? And all of your fancy lattes and cappuccinos and frappuccinos and iced coffees and stuff like this all have a different type of milk. You have oat milk and almond milk and soy milk and whole milk and skim milk and all these different types of milk. Well, maybe in that case, milk is an attribute describing the drink you're making, right? And values of milk would be oat, soy, whole, skim, whatever, right? So it depends. And this is something that is not a syntactical thing. This is not something that you would catch this error just by looking at the model. You only catch the error by really understanding the business process, right? So it can be a little trial and error. It can be a little bit of this kind of going back and forth with the business people or with the other analysts or whatever, and just kind of figuring out what's going to make sense for this particular case. And this is something that I hope maybe you started to kind of see, and this is why I asked you guys to start making up some sample data in assignment 1, because often I find that people will identify values and start writing values as if they're attributes of your entity. But then when you start trying to create values for that, right? Maybe you've got an entity that is car, right? And attributes of your car might be, make, model, year, and color, right? But I would see people that would have attributes of car like make, model, red, blue, 4-wheel drive. And I'm like, okay, so what's a value for the attribute red? There's not a value for red. Red is a value of an attribute like color, right? And this is something that when you start populating data becomes kind of immediately obvious, right? So that's one of the things that hopefully you kind of took away from assignment 1. All right, so we have a couple of examples here. This example is from your book, or kind of a modified, simplified version of what's in your book on page 120. So we're going to model this kind of simple story here. There are several colleges in the university. Each college sounds like an entity to me, has a name, location, and size. A college offers many courses, which are described by course number, name, and credit hours. College also has several instructors. Instructors teach courses, but not all instructors are scheduled to teach during all terms. All courses must be taught by an instructor. Instructors are capable of teaching multiple courses offered by the college. Instructors have a unique employee ID, name, qualification, experience are also recorded. So I hear a lot of attributes here, a lot of things that might be entities, might be attributes, might be relationships. I'm not really sure just yet. So someone who hasn't had the great data modeling training, you guys, and the expertise that you guys are already developing, might read this story and come up with something like this, right? That a college has instructors, and maybe instructor is a composite attribute made up of all these things that describe an instructor, like a name, qualification, experience, and employee IDs. And all of these things that we talked about are just attributes of this one entity, college. Now, this is syntactically okay. All right, just at a glance, there's nothing, if you took all these words off here and you didn't know what the business story is, you look at this and yeah, we're using all of our ER modeling grammar elements correctly. But we have a semantic problem here because it did say colleges can have multiple instructors and courses, and currently we can only have one value for instructor and course. So we could fix this semantic problem by just simply making instructor and course multi-value attributes. Okay, we fixed that semantic problem. Great. Still syntactically okay, but there's also another problem here, another semantic problem here, that the story is described that instructors can teach courses. Okay, that there should be a relationship here, not just that instructors work for colleges and courses are offered by colleges, but there's a relationship here. So maybe we go back into our modeling grammar toolkit and we throw a relationship here between this multi-value attribute and this multi-value attribute. And at this point, we are syntactically incorrect because this is an incorrect use of the grammar. And anyone who knows data modeling, even if they don't know anything about the story at all, they can look at this and go, no, this isn't right. There's an error in your modeling because you can't have a relationship between attributes. So I'm going to suggest that this might be a better way to solve this. So maybe instructors are not an attribute of college, but all of these attributes that together make up an instructor are attributes of another entity, in this case called instructors, right? And we have a one-to-many relationship with, between instructors and colleges. Instructors are employed by exactly one college, and a college employs a minimum of one and a maximum of many instructors. That seems reasonable. And then courses, so course number, name, and credit hours, not attributes of college, but attributes of this courses entity. And a course is offered by exactly one college, and a college offers between one and many courses. And now we can put this relationship between these entities of instructors and courses. Okay, a course is taught by exactly one instructor. An instructor teaches a minimum of 0 and a maximum of many courses. Because I'm pretty sure in the story it said that instructors can teach multiple courses, and somewhere it says that, yeah, not all instructors are scheduled to teach during all terms, right? So that's saying to me that an instructor does not have to be teaching a course all the time, so that's our optional participation. But if they are teaching, they can teach many courses. So now we're syntactically incorrect, and we are semantically incorrect, or we are semantically correct in that we are capturing all of our business requirements in this model. So that's the example from your book. I have an example from my life, though, because anytime I'm using any of my technology or anything around me, I'm always thinking about, what does the data back end of this look like? It's a weird way to live your life. I hope you guys come into the light with me, or the dark side maybe with me. Start thinking, man, what would a data model for my car or my phone or my wristwatch be, you know? So I'm looking at the list of contacts in my phone. I'm adding, I met this person and need a shower, and she's like, here's my number, 555-542-6645. I'm putting this in my phone, and I'm like, you know, obviously this contact app on your phone has some type of database that it's storing data in, right? There's a database on your phone, keeping track of your contacts and your web browser history and all that. So I'm like, what does this data model for the contact app look like? And I'm seeing, you know, I can put a name, put a phone number, an email address, and this groups and ringtones. We'll kind of ignore that for just a minute. And as I'm experimenting with this, I noticed that I can just create an individual contact, an individual user, but I'm required to put something for the name, but I can actually do just a name with nothing else. I don't have to put a phone number. I don't have to put an email address. So I'm thinking name is probably a required or a mandatory attribute. Email and home phone number are optional attributes. And I also did a little checking around, and I noticed that I could create 2 or more contacts with the same exact name, right? So if you know 3 people named John Taylor, you can put 3 John Taylors in there. Okay, so that says to me name is not our primary key, not our unique identifier. There's probably something else that the app is doing in the background, some contact ID number that we're just not seeing. So this is my current kind of understanding of the data model for the contacts app on my phone. This is syntactically correct, right? This is how we use the grammar. But does this capture all of the business rules from this contact app application? So I click around a little bit more, and I notice that if I click on this little plus sign next to phone, I get a whole list of, well, not just home, but we can have a phone number that's mobile, work main, work fax, home fax, pager, or other. Okay, so I can put someone's mobile phone number and add another one as their work phone number. I can put multiple phone numbers for this person. It's all optional. Having them all is optional. But now in my head, I'm thinking maybe this is more what the model looks like, right? Contact ID is required, name is required, but email, home number, mobile number, work number, main number, work fax, home fax, pager, and other are all just optional attributes. Syntactically correct. As far as I know right now, this seems to be capturing all the business rules. I think it's a little bit ugly because I've got a lot of attributes here that don't have any values for most of my rows. That's something we want to try to avoid in our database design. We're going to come back and talk about that more later. So I'm not sure, but I think this captures the business rules as I see them right now. But then I notice this, create custom type. So I click on that, and I see that I can type anything I want in here, right? So it's not just home, mobile, work, fax, pager, and other. I can have she's got a helicopter or a submarine. I can put whatever I want there. The options are unlimited. So now, does this data model make sense? Can I just have an infinite number of attributes describing different types of phone numbers a person might have? That doesn't really make sense. So maybe it's not that we have multiple attributes describing someone's phone number, but maybe phone number is what? Yeah, maybe phone number is a multi-value attribute. And as we just discussed, a multi-value attribute isn't actually an attribute. A multi-value attribute is represented by a weak entity, in this case phone numbers, that's in a relationship with an individual contact, right? So in this case, a phone number that we're storing over here belongs to exactly one contact, and a contact can have a minimum of 0 phone numbers, right? Because we said having any phone number is optional, and a maximum of many phone numbers. So we have a partial key of number and contact ID, which is the primary key in contacts, is now over here in our weak entity as a foreign key that refers back to this contact ID. Contact ID and phone number, our partial key together, makes up a composite primary key. So the combination of contact ID and phone number uniquely identify each row in this table. And then we just have another attribute called number type, which the value describes what type of phone number this is, right? And so this is why, so we have these values of like home, mobile, fax, cell phone, things like that, that are pre-populated. But this is what's allowing us to type just anything at all we want for number type, because that's just a value of this attribute. So I think this is probably more what our data model for this contact app looks like. But you may be saying now, isn't phone number unique? Shouldn't number just by itself be able to uniquely identify a row in this table? I think some apps probably use phone number as a unique identifier. I don't think that's a very good practice, though. Oh, we just went through this. Because take, for example, this case, where we have contact 102, Jane Smith, and contact 104, Dave Rogers. They both have this same phone number, 555-334-3434, as their work number, because I guess they probably work at the same place, and maybe that's just the phone number for the front desk, right? But if you say contact ID 102 plus this phone number, you know you're talking about this row, and contact ID 104 plus this phone number, we know we're talking about this row. So the two things together uniquely identify every row in this entity. Yeah. Syntactically correct, semantically correct, capturing all our business rules. I like it. So I already mentioned a little bit about this, about assignment 1, but this was one of the goals of assignment 1 was to take a system like your cell phone, right? Or like Uber or like Netflix, and kind of think about, at a very high level, like what does their database design look like? Like how could I create a database that would do something like what Uber does or Netflix does or like what Chase Bank does to keep track of all of our customers and bank accounts and loan agents and things like that. And it's important to note that as an outsider looking in, you're going to do it wrong. Like you're not going to get this right. You're not going to design the database the same way that the database is actually designed, right? Because for one, people, even with the same business cases, are going to design these things a little bit differently, but perhaps even more importantly, or a bigger impact, is what you see when you're using the app is only the external schema, right? The external schema is what's presented to you as a user or to an application. Everything that's modeled at the conceptual level is kind of hidden away from us, right? So there's going to be a lot of details and a lot of stuff going on under the covers that we just simply can't see. Now, we could create a database design that might have the same effect and give the same benefits, but it's going to be different because, only seeing the external schema, we can't see what's going on beneath that. Yeah, and this is what I just said about determining if something is an entity, an attribute, a value. Can be a judgment call, can be tricky, and can come easier with experience. So semantic errors are when we do something that's not properly capturing our business case, right? So for example, modeling our contacts with a whole bunch of phone numbers instead of modeling phone number as a multi-value attribute and ultimately a weak entity that's connected to the contact. Syntactical errors or syntax errors are easier to spot when we're using our grammar incorrectly. And we manage errors by going through our business cases and kind of understanding when something stops making sense and saying, oh, well, how do we model this to actually capture what the business intends to do? And with that, I believe we are wrapped up with chapter 3. Okay? And so we're skipping chapters 4 and 5 because they go into some different depths on the entity relationship modeling. And we're going to skip into chapter 6, where we're going to introduce this idea of the relational data model. And so this is taking us from the higher level conceptual constructs into our relational and logical models that are going to allow us to start creating our DDL code and doing something that we can technically implement in a database management system. So we're going to talk for a moment about why we should care about this, and then we're going to learn a little bit about these terms that we use in relational data modeling, like relation, tuple, cardinality, and degrees. And this is weird because we've already talked about a lot of these terms, particularly cardinality and degrees. But this may be a little confusing because we're actually going to introduce some new definitions of these and some new ways of thinking about these. And when we first introduced this idea of the degree of a relationship, and we said that's just the number of entities that are participating in the relationship, and you guys were super good at identifying like 1, 2, 3. Oh yes, 3 entities participating in the relationship, so the degree is 3. Pretty simple. And I told you we would come back to this idea and see that, oh, this actually has a bigger meaning in the story. So that's what we're learning about now. So the relational data model. I think we already talked a little bit about Ed Codd, who worked for IBM in 1970 and was the father of the modern relational database management system. So he was a mathematician by training, got to seeing how important data was becoming to businesses, even in the 70s. He was very forward-thinking in this way. And he saw that everyone was just kind of managing data and storing data in haphazard ways. Every developer who was writing an application or storing stuff on punch cards or on magnetic tape or whatever was kind of coming up with their own approach to storing the data. And so he went into his mathematical tool belt, used set theory, and developed this relational data model. So in the relational data model, we have things called databases, which are collections of relations. These relations are two-dimensional tables that are made up of rows and rows and columns, where your columns are attributes, and each row or tuple is a collection of related data values. And your values are at the intersection of your rows and columns. Okay, so a relation is a two-dimensional table, a tuple is a row within this table, and an attribute is a column in the table, and then the domain is the set of possible values of an attribute. So your book has this statement. It's a big, bold statement. It's a very rah-rah about relational databases, but I think it is important enough that I'm going to read it. The foundation of modern database technology is, without question, the relational model. It is the foundation that makes the field a science. A science. It's based on math. Thus, any book on the fundamentals of database technology that does not include a thorough coverage of the relational model is by definition shallow. Likewise, any claim to expertise in the database field, which is what you guys are after, can hardly be justified if the claimant does not understand the relational model in depth. So this is why we don't just jump right into writing SQL. Like, we could start learning SQL on the very first night of class, but what you're going to find is if you've got that shallow understanding, as we get into deeper and deeper and more complex problems, you're quickly going to reach the limits of what you can do with that tool. So we're starting with the modeling, we're moving into the relational modeling and the data definition language stuff, and then that's going to build us a good foundation for our SQL. So this is the next step beyond our conceptual modeling, where we are just, we mentioned this as being technology independent, right? This is just our pictures that are representing our business rules. When we move into our logical data modeling, we're getting to the point where we can start kind of translating this into our data definition language code and actually implementing it in our database management system. Yeah, so it serves as a transition from the technology independent to the technology dependent. That's kind of what we're saying here. All right, so our conceptual modeling uses many of these same terms that we've already talked about, but in a slightly different way, right? Cardinality we're going to understand by the end of the night a little bit differently. Degrees of relationships and of relations, and that relations and relationships are different things, but also kind of the same thing, like they're kind of related to one another a little bit. It's going to get deep, guys. It's going to get deep. Guys, look at your hands. All right, so we already talked about this. Relation, tuple, attribute. Here's the new stuff. The degree of the relation, where we previously said the degree of a relationship was the number of entities participating in the relationship. We're now saying the degree of the relation is the number of attributes in the relation. And the cardinality of the relation, where we previously said cardinality was either you participate a maximum of one time or a maximum of many times, we're now going to understand the cardinality of the relation to be the number of tuples, or the number of rows, or the number of instances in the relation. So our relation is made up of a heading, which is the very first tuple at the top here. And this is also known as the schema of our relation. So we have the name of our relation, and then all of the attributes that make up this relation. And then the relation also has a body, which is just a set of all the other tuples that contain our data values. Okay? So in this case, we have this relation called plants that has these 1, 2, 3 attributes, plant number, plant name, and budget. And since it has 3 attributes, we would say the degree of this relation is 3. Excellent. And we have 1, 2, 3, 4, 5 tuples in this relation. So our cardinality is 5, right? Here we have a plants relation with 3 attributes. So the degree is 3, and our cardinality is 4, number of tuples. Good. See, it's math. Very simple math right now. All right. So we're changing up this, our understanding of degree, right? We used to say it's the number of entities participating in a relationship. Now we're saying degree is the number of attributes or columns in a relation, but why? So recall that we previously said an entity is just made up of a collection of attributes that are related to one another. Okay? So imagine that each attribute of an entity, since attributes are just, or entities are just made up of attributes that are related to one another, maybe each attribute is not an attribute, but each attribute is its own entity that's associated with other entities, and together all of these entities come together to make up this, this bigger construct, right? So instead of employee being employee ID, name, and phone, these 3 attributes coming together, what if each one of these attributes was stored in its own entity, and then we just had a relationship between employee IDs, employee names, and employee phone numbers. Now, this is a crazy way to model this. We could do this. This would be very inefficient. But in this case, what would the degree of this relationship be? 3, because we have 1, 2, 3 entities participating in the relationship. And the degree of this relation is 3 because we have 1, 2, 3 attributes making up the relation. So that's why the degree of a relation is the number of attributes, and the degree of a relationship is the number of entities making up a relationship, or the number of entities participating in a relationship. Kind of a different thing, but actually kind of the same thing when we think about it like this. Let me give you another example of how this works. So when we had this many-to-many relationship between dependents and hobbies, what is the degree of this participation relationship? 2, right? Because we have 1, 2 entities participating in the relationship, okay? And recall that we decompose this many-to-many relationship into these 2 one-to-many relationships with this gerund participation sitting in the middle, okay? What is the degree of this relation participation? 2, because we have 2 attributes making up this relation. So this participation relationship, which has a degree of 2, is really, when we start creating it in the database, going to be a gerund or a table in our database that also has a degree of 2, right? So that relationship is really this relation. It's all kind of the same thing, just different ways of thinking about it. Neat. And so we can also, we can see this same thing play out. We don't need to use a gerund to decompose a one-to-many relationship, but we could, and we would get the same exact thing, right? We have a relationship here with 2 degrees. If we put a gerund in between them, we're going to get a gerund that has 2 degrees as well, two attributes. Cardinality. So we say now, instead of cardinality just being 1 or many, we're going to say cardinality is the number of tuples or rows in a relation, right? So when we say things like many students take a class, what do we really mean by that? Like many, could many students, like in an unbounded sense, take this class? No, we couldn't have, like what's the biggest reason, or the first reason maybe, that we couldn't have 1 million students take this class?
Professor, only one.
There's only one of me and I couldn't talk that loudly? What if I could talk infinitely loudly? I could teach 1 million students all at once. Why can't we have 1 million students enroll in this class?
Infrastructure.
What's that?
Infrastructure.
Infrastructure, okay, so that would be something that would get in the way. But let's say we had a really big room that we could fit 1 million people in.
You cannot keep a record of who's attending, who's not.
What's that?
You cannot keep a record of all the people attending.
Okay, it would be hard to do. So imagine I had infinite resources to keep track of roll and everything. Why can't 1 million people enroll in this class? It's not allowed. We probably won't allow it. There's a technical reason. There's a real hard reason we can't have 1 million people in this class.
Maybe they can't answer all the questions.
You guys are thinking very pragmatically. You guys care about me, I can tell. This is like, don't do that to poor Dr. Grimes. You can't handle 1 million students. How many students attend the University of Houston? Like, I don't know, like less than 1 million. Yes, less than 1 million. It's like, I don't know, 40,000 or something like that. right? We can't have 1 million students enroll in this class because there's not 1 million students to enroll in this class, right? So what we're really saying when we say many students can take a class is any number of students up to the number of students we have enrolled at the university may take a class, right? So the cardinality of students taking this class isn't really many. It's really 40,000, 43,700, however many students we have, right? Which that's going to be the cardinality of the student relation. Now, as you guys have very adeptly pointed out, there are going to be a lot of other business rules that are going to limit how many students we enroll in the class, right? I think this room holds 48 students or something like that, right? So we're going to have a business rule in place for that. We're going to have business rules in place to keep our professors, sane so they don't have to teach 40,000 students all at once, right? But the real hard, fast limit that we can't have, 1 million students is that we don't have 1 million students to enroll. So when we say many, we really mean anything up to the number of tuples or instances we have in this table. So now, back to our many-to-many relationship between dependents and hobbies. We have this dependent relation that has these 1, 2, 3, 4 attributes. So we would say the degree of this is 4, and the cardinality is 5, okay? For hobbies, we have a degree, again, of 4 and a cardinality of 5, okay? And then participation, our gerund, we said the degree is 2, and then the cardinality is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So we have a cardinality of 14 here. So I suppose there is some utility in this. There is some value in just being able to count how many rows are in a table, right? Yeah, I guess useful to know like how much stuff you've got. But there is another perhaps more important and more valuable thing that we can understand here, right? Because by understanding the cardinality of these source relations, we can determine worst case scenario how complex any join operations might be. So if we have 5 dependents and 5 hobbies, what is the maximum cardinality of this participation relation if every dependent participates in every hobby? 25, right? Because it's 5 times 5 is 25. And that's not a very big number, right? But imagine if you're, Facebook or something like that, and you have, not 5 people in this data set here, but we have 100,000 people in this data set, right? And then we have, 5,000 clubs that these 100,000 people could each be in, right? Now we've got a maximum cardinality if we say we have 100,000 users and there's 5,000 clubs that they could potentially be in. Worst case scenario, when we join that together, we're going to have 100,000 times 5, what is that, 5 billion, 500 million, whatever it winds up being, possible combinations. And then if there's a third table that has, 10 different meeting locations or something that those clubs could meet in, well, now you're at 500 million times 10 up to 5 billion possible combinations. That gets very big and hairy and difficult to solve pretty quickly. So the value in understanding our cardinality here is to say, okay, now before we do this join operation that could result in up to 5 billion combinations, is there something we can do to reduce the cardinality of these relations before we join them together, right? Because if we wanted to say something like, we're only interested in the hobbies that our female dependents are doing, right? And we can get rid of all of our male dependents before we do the join, then we're going to be starting with a relation that has a cardinality of 2. And even, worst case scenario, if 2 dependents are participating in all 5 hobbies, we're going to get a maximum cardinality of 10 instead of 25, right? So the point being, anything we can do to reduce the cardinality before we do these joins is going to make our joins much more efficient. That's why we need to know this. All right, so we care about logical data modeling because this is taking us from our high-level conceptual modeling into something that we can actually implement in our database. We talked about a relation being this 2-dimensional table where we have columns that are attributes and rows that are tuples or instances in our ER speak. We said cardinality is not just that an instance can participate many times, but we're actually describing the number of instances of an entity or the number of tuples in a relation. So the number of tuples in a relation is our cardinality, and degree is the number of attributes in the relation. You guys may need a minute to let your head settle out. Any questions? All right, so it is 7:15. Why don't we take these 10 minutes, and we'll take 10 minutes on Zoom for everyone to zoom around and kind of stretch our legs, get some water, use the restroom, whatever, and we will reconvene at 7:25. Welcome back, everyone. As we get into Module 6.2, we're going to kind of break down a little bit more specifically what a relation is. So we're going to describe the characteristics of a relation, talk a little bit about naming conventions, and then we're going to get into our set theory operators, and we'll talk more about kind of how we use those in the next module. But recall we said a relation is this 2-dimensional table with attributes and tuples, and at the intersection of our attribute and tuples are values. So a relation is our mathematical term representing a 2-dimensional table, has a heading, which is a single tuple containing the name of the relation and our attributes, which is also known as the relation schema, and then has a body which is made up of all of our data value tuples. So we've already said all of this stuff in previous slides. It's important to know that attributes of a relation have to have unique names. Okay, so within our relation, each attribute name has to be unique. We can't have 5 names or 5 attributes all called name. And values of an attribute in a relation come from the same domain. Okay, so for example, if we have an attribute called name, right, all of the values for that attribute represent people's names. You're not putting like someone's name and then someone's phone number and someone's gender and someone's height all in this one attribute we call name. Okay, so values of an attribute in the relation all come from the same domain. These next 2 things I think are particularly interesting because they seem kind of counterintuitive and weird. First, the order of the arrangement of the tuples does not matter, and the order of the attributes does not matter. So when we store data in our relation, all of our tuples or all of our rows or all of our instances, these are all kind of the same idea, are just stored in kind of a random order, no particular order. Same thing for the attributes. Even though we may define them in a particular order, your PeopleSoft ID, first name, last name, address, phone number, whatever, they're not actually stored in any particular order in the database. Now this sounds like a bad thing, because if they're in no order, it's going to be hard to find what you're looking for. But the benefit of this is that since they are not stored in any particular order, when we query the data, we can define the order that we want to see the tuples or the order we want to see the attributes without any performance penalty. So we can rearrange and reorder without incurring any cost. Now, if any of you stick with me next semester and take Business Analytics 6356, we'll see that this is not always the case with some of these new emerging non-relational databases, and that's a way that they can have higher performance for certain queries, but then certain other queries will actually have performance that's much worse than a relational database. So a relational database kind of tries to give you consistent performance by having no particular order for the tuples. Now, if you've done any work with databases before, you may be ready to call me out on this a little bit and say, but if we are interested, if we know we're going to be interested in getting the tuples back in a certain order, we can accommodate that through a technique called indexing. So by creating indexes, we can specify an order that we're going to be wanting to access the tuples in, but still the tuples themselves are stored in just no particular order. So in the relation, the order of the attributes and the order of the tuples does not matter. Every value for an attribute in a tuple is atomic, so composite and multi-value attributes are not a thing that actually exist in our relation. Okay, so we already talked about this with multi-value attribute. Similarly, composite attributes are just a modeling construct. So when we say name is made up of first name, middle name, last name, those three atomic attributes, this idea of name, the composite attribute, doesn't actually exist, right? That's just something that we're saying to kind of make it make more sense to our human brains. We're only actually storing the atomic values that make up that composite attribute. Derived attributes, attributes we calculate, are not captured in our relation, right? Rather, we capture the value of the attribute from which the derived attribute is derived, right? So an example of a derived attribute might be age. So we don't store your age in the database. We store your date of birth in the database, and we derive your age by subtracting date of birth from today's date. Okay, but derived attributes are not captured in the relation. And all tuples in the relation must be distinct, okay? So we can't have any duplicate tuples, and effectively what this means is that there must be some combination of attributes, one or more attributes, that we can use as a unique identifier, okay? We can't have any duplicate tuples in our relation. We'll have examples of most of this stuff throughout the rest of the evening. So naming conventions, attribute names, we already said, must be unique within a relation. Additionally, attribute names must be unique across the entire conceptual schema, right? Basically across our entire database. However, ensuring that this is the case is not really that big a deal, because typically within your DBMS, your attribute name is going to be prepended with the name of the relation or the name of the table, which also has to be unique across conceptual schema, such that you've got relation.attribute name. So if your attribute name is unique within the relation and the name of the relation is unique, the combination of these two things is necessarily going to be unique, right? Yeah, so if you had like a customer relation and a pets relation, right? Like in our Dave's dog washing thing, customers and dogs, both the customer's relation and the dog's relation could have an attribute called date of birth, right? Because you've got dogs.date of birth and customers.date of birth. And so they would wind up being unique. Page 283 of your book suggests a possible naming convention in that there's a three-letter prefix that represents the name of the relation, then an underscore, and then something that corresponds to the attribute name. It's a perfectly fine naming convention, but I would suggest that it's not something that you really need to commit to memory or say this is the naming convention that we have to use for our database, because there are many naming conventions that you'll find other people using and other books describing and other businesses using in the real world. The important part is that we do have a naming convention and something that is meaningful and structured and robust in such a way that we can look at the name of an attribute and understand what it is. And is this a foreign key that's going to be referring to another attribute, and what table does this attribute belong with? Things like that. So a lot of different naming conventions. I wouldn't put so much stock, but I do bring this up just to make some of the examples in the book a little bit more a little bit easier to understand, right? That PL underscore budget, this is because it's the budget for a plant, and this is going to be in the plant entity, right? All right, so on to set theory and relational algebra. So as we've talked about, relational databases are based on set theory, and manipulating these sets, or the technique we're going to use for manipulating these sets, is known as relational algebra. So we're going to talk about 3 set theory operators: union, intersection, and difference. Union being the combination. Imagine each one of these circles as being a data set, right, that has some overlap. Union being everything in both data sets. Intersection being where the 2 data sets overlap. And the difference being where we have data points that are in one data set but that are not in the other data set. Okay, so we have these 2 data sets. Let's say one is people that are from Houston, right? So I think it's fair to say some people are from Houston. We also have some people that attend the University of Houston, right? And there is some overlap in these 2 data sets, right? There are some people from Houston that attend the University of Houston. There are some people from Houston that don't attend the University of Houston. Poor guys. Feel sorry for them. And then there are some people that attend the University of Houston that are not from Houston, right? So we kind of have 3 different situations that people could be in. So the union, this is basically our OR operation, is people that are from Houston or attend the University of Houston, right? So if you're from Houston or you attend the University of Houston, you would be in the union of these 2 data sets. The intersection is people that are from Houston and attend the University of Houston. Okay, so this is like our AND operation. And then the difference can work in either direction. We have people that are from Houston but do not go to the University of Houston, or people that go to the University of Houston but that are not from Houston. I bet in this class we probably have people in all 3 of these segments. Difference. Is this I think our in-class exercise is coming up. I'm trying to remember the order here. Yes, in-class exercise. All right, so we're going to operationalize this set theory example with some data. So hopefully, boy, sure doesn't look like my thing is working. Oh, look at that. Sometimes Poll Everywhere just likes to take its time. So we should have a Poll Everywhere activity activating. Yeah, there we go. So we have some sample data here. We have 6 students with student IDs, names, their hometown, and their school. So how many people are in the union of Houston being their hometown and they attend the University of UH? We're in the union, so they're either from Houston or they attend UH, and we can answer on our thing. Let's see. Let's see, I think I need my mouse over here. Which way do we go? Oh, there we go. Oh, here we go. All right, so we have a lot of results coming in. Let's flip over and see how everyone's. Ooh, a little bit of dissension here. 2, 4, or 6. Okay, so how many are in the union, meaning they are from Houston or they go to the University of Houston? So would this person be in the union of these 2 data sets? Yeah, because they're from Houston. What about this person from Dallas? Would they be in the union of these 2 data sets? Yeah, because they attend UH. This person attends UH and is from Houston, so they're going to be in the union of these 2 data sets because they're in both the data sets. From Austin attends UH. Are they in the union? They're in the union. Houston and Rick? What's this? Rice? Is that a university here? Houston and they attend Rice. Houston and they attend Rice. Yeah, all 6 of these people, 96% of you agree. We have one holdout. One person demanding that it's 4. No. Oh, you guys are all 100% right. that the union of these two data sets is 6. All right, let's take a look at another one. There we go. How many are in the intersection of being from Houston and attending UH? So they're from Houston and they attend UH. Oh, so this person just really likes the number 4. They're going for 4. 96% of you think that it's 2. And as I'm looking at this, it looks to me like Adam and Chris would be in the intersection of their hometown being Houston and attending UH. Right? Eunice and Frank are from Houston, but they attend Rice. These two people are from UH, but they're from Dallas and Austin. So 2 is the correct answer. 100% of you know it. Up next, there we go. How many attend UH but are not from Houston? So this is the difference. Looking for those that attend UH but are not from Houston. I just realized this may be difficult for those of you on Zoom to see, because I know sometimes there's a little bit of a reflection kind of right here in the way, but we'll be posting this, this video soon. And I think most of us agree that it's 2. Let's see. See if the 3 crowd is going to win out here. So Beth and Dave, both from UH, or both attend UH, but are not from Houston. So 2 is the correct answer. And then last but not least, going in the other direction. Oh, there we go. Going in the other direction. How many are from Houston but do not attend the University of Houston? So this is just our difference in the other direction. A lot of people converging around 2. And yeah, I see just these 2 people here that are from Houston, but attend a university other than the University of Houston. Excellent. Good job, guys. So that's our kind of basic set theory operators of union, intersection, and difference, right? So those are our 3 set operators, and we'll be talking about those a little bit more as the semester progresses. Importance of naming conventions. We looked at one potential naming convention, but this is going to vary a lot from kind of business application to business application. But the point is, we need to make sure that we have something that's meaningful and understandable and robust to capture our attributes and entities. And then we said the relations have a number of characteristics, like that they are a 2-dimensional table made up of attributes and tuples, and at the intersection of our attributes and tuples are data values. What did we say about the order in which the tuples and the attributes are stored?
No order.
Yeah, it is no order, right? It's just kind of randomly thrown in there, which actually is kind of nice because when we query it, we can then define the order that we want these things returned in. Let's see. We said we can't have multi-value attributes. We can't have composite attributes. It's only one atomic value at the intersection of an attribute and a tuple. Is there anything else interesting we said about a relation? We said the relation has one tuple at the top, which is the heading or the relation schema, and then the rest of the tuples make up the body. And yeah, I think that's kind of the big points there. I don't know where my mouse is. There we go. All right. So that is module 6.2. And then 6.3, I think, is our last module for the night. Let's see. Oh, no, we have 2 more modules, 6.3 and 6.4. Oh, it's OK. We got plenty of time. We got nothing but time. Time for databases. All right. Module 6.3, we're going to start talking about data integrity constraints. And this is going to be key to your understanding as we talk about a whole bunch of different types of keys that provide these data integrity constraints, including superkeys, candidate keys, key attributes, non-key attributes, primary keys, and alternate keys. This is going to lead into our discussion of the entity integrity constraint, the referential integrity constraint, and the foreign key constraint. Okay, and now we're going to start putting some definition behind some of these things like foreign keys and primary keys that we've been kind of tossing around very loosely for the past couple of hours. Come on, computer, don't let me down now. All right. So our data integrity constraints are rules that we implement within our database in order to make sure that the database conforms to the business rules and requirements that we've talked about. So they're technical expressions of our business rules that kind of enforce that the database is going to do what the business needs it to do. This works across our conceptual, logical, and physical modeling and is considered to be a part of the schema. So we have these four types of keys that we're going to be talking about that describe the uniqueness of our tuples: superkeys, candidate keys, primary keys, and alternate keys. So a superkey is a set of one or more attributes which, taken collectively, uniquely identifies a tuple of a relation. So we say a superkey has the property of uniqueness. Okay? So we previously said, when we were talking about, oh, this is one we didn't mention, properties of a relation. One of the properties of a relation that I forgot to bring back up is that all tuples have to be able to be uniquely identified, that we can't have any completely identical tuples, right? So by virtue of that, it's going to be a given that every attribute in the relation, if we take the value of all the attributes, that is going to be, that combination of attributes will be able to uniquely identify every tuple in our relation, okay? So we're always going to have at least this one superkey, which is every attribute in the relation together, okay? So if we're thinking about your student record in PeopleSoft, right? And you've got your PeopleSoft ID, your first name, your last name, your email address, your phone number, your hair color, and your eye color all stored in this relation. All of those attributes taken together can uniquely identify you, right? That is a superkey. Probably some smaller set of those attributes. You probably don't actually need your hair color and your eye color to uniquely identify you. Probably just PeopleSoft ID, first name, last name, and email address and phone number could uniquely identify you. Probably don't even need all that, right? Like PeopleSoft ID, first name, and last name. Probably just your PeopleSoft ID could uniquely identify you, right? Point is, we have a lot of superkeys, right? And we can take a bunch of attributes out of superkeys, and they're still superkeys. They still have this property of uniqueness, right? So not every attribute in a superkey contributes to it being unique, right? But we can have a lot of attributes in there. So we start with every attribute in the relation, and we can kind of simplify down from there until we get to some set of attributes that if we take anything else away from it, it no longer would be unique. And that's a candidate key. A superkey with no proper subset that uniquely identifies a tuple in a relation. Okay, so a candidate key has these two properties, uniqueness and irreducibility. It cannot be reduced any further, right? So like your PeopleSoft ID is a candidate key, right? Well, it's just one attribute, so we can't reduce it any further, and it uniquely identifies you, right? Or in the case of our modeling the contacts app on my phone, the phone numbers entity had three attributes, right? The contact ID, the phone number, and the phone number type, those three attributes. Those three things together are a superkey, right? But we didn't really need the phone number type, just the contact ID and the phone number together uniquely identified each phone number entry. So that was our candidate key, and we could not reduce that any further, and that maintained its uniqueness. So a candidate key is a super key with no proper subset that uniquely identifies a tuple of a relation. Proper subset. We should define this because this is going to come up a couple of times. So let's imagine that we have a set of 3 values, A, B, and C, right? So A, B, C is a subset of the set A, B, C. Okay, a set is a subset of itself. However, a set is not a proper subset of itself. Okay, so we have proper subsets of A, B, C would be A, B, C, AB, AC, and BC. Right? So we have 6 proper subsets of this set ABC. And then ABC is a subset of ABC, but ABC is not a proper subset of ABC. Okay? So this idea of proper subsets versus subsets is going to come up a couple of times in this discussion. Okay, so a superkey with no proper subset of attributes that uniquely identifies tuples of the relation. Okay, so we're going to have a whole bunch of superkeys. We're going to have some smaller number of candidate keys. And then from our set of 1 or more candidate keys that we identify, we're going to kind of bless one of them, or we're going to identify one of them as being our primary key. And this is a candidate key with no missing values for any of the constituent attributes that make up that key, right? So we have the property of uniqueness, super key, property of irreducibility from the candidate key, and also the entity integrity constraint. And this is just saying that we cannot have any missing values. We cannot have any null values, okay? So our candidate key is an irreducible unique identifier. Our primary key is a candidate key that we have selected to be our primary key. And once we do that, we can never have a null value for that candidate key or for any of the attributes that make up that candidate key. And then our alternate key is any candidate key that is not serving the role of the primary key. So we might have multiple candidate keys. We might only have one. We're going to select only one of them to be the primary key, and then any candidate keys that we didn't select as the primary key, we will call an alternate key. All right, so we have 2 samples, or 2 examples here from the book. And the basic setup here is that we have some, this is like a prescription number, so an ID number identifying prescriptions that a doctor writes. We have a patient identification number. We have a number of medications here. I think this is like penicillin, Tylenol, Claritin, aspirin, Zantac, something. Valium is in here somewhere, right? These are medications that might be prescribed to a patient. And then we have a dosage, taking 2 or 3 of this given pill. So if you look through this data, I think you will come to the conclusion, and I'm just going to tell you that this is the case, that prescription number is a unique identifier. Okay, if I say point to the row that goes with prescription number A105, this is the row. Okay, that is a unique identifier. A108 is this row. There's not another A108 anywhere. Patient number, this is not the case, right? Because we have patient number 7642 twice. We have patient number 4772 showing up multiple times. Patient number 7384 showing up multiple times. So this is not a unique identifier. However, as is described in the business case in the book, if we combine the value of patient number and med code, these 2 things together are a unique identifier. Okay? So what we're basically saying, kind of in the business terms here, is that a patient can only be prescribed a certain medication one time, right? Our prescription, each prescription is going to be for a single patient and a single medication, and a patient can only be prescribed medication a single time. That's effectively what's happening here. So now let's figure out what our superkeys for this relation are. So kind of the most basic and the most straightforward is going to be just prescription number, right? It has the property of uniqueness. That's all we care about for a superkey. And then we can add any other attributes to a superkey, and it's going to remain a superkey, right? So something like prescription number and patient number together, these two attributes are a superkey together. Similarly, patient number and prescription number and med code would be a superkey. Prescription number and dosage would be a superkey, right? Because if I tell you point to the row that is A101 and dosage is 2, well, it's going to be this row right here. This didn't really help us understand that because this is already a unique identifier, okay? A104 and 3 dosage, well, that's right here. It's a superkey. Another superkey would be this combination of patient number and med code, and then anything we can add to that, like patient number, med code, and dosage, or patient number, med code, and prescription number. Or going all the way, patient number, prescription number, patient number, and dosage, I missed one. Prescription number, med code, and dosage, or then even all 4 attributes together, prescription number, patient number, med code, and dosage would be a superkey, right? Because if you know the values of all 4 of these things, we can uniquely identify the tuple that we are interested in. So we have a lot of superkeys here, which is great for identifying individual tuples, but we can simplify things a little bit, right? So the general statement here, if some set of attributes K is a superkey, then any superset of K, that's any set that contains K, is also going to be a superkey. So superkeys are good at uniquely identifying tuples, but there's lots of them, too many of them, more of them than we need. So we're going to simplify things by reducing our superkeys until they are irreducible, and that's going to be our candidate key, okay? So what about prescription number? Can prescription number, is there a proper subset of prescription number that can uniquely identify all the tuples in our relation? Could ask this another way. If we have a set that has only one item in it, is there even a proper subset of this set? Because you can't have a proper subset of a set that only has one item. So is there a proper subset of this superkey that is still unique? No. So that means this is a candidate key because it is unique and it is irreducible. Now what about this set of attributes, prescription number and patient number? Can we reduce this? Is there a proper subset of attributes of these 2 attributes that is still unique? Yes, just prescription number, right? We can reduce this by removing patient number. So no, this is not a candidate key. Okay, what about this set of attributes, prescription number and med code? Is this irreducible? It's not irreducible. We can reduce this and it still remains unique. We can get rid of med code and just have prescription number, so this is not a candidate key. Similarly, prescription number and dosage together, not a candidate key because the proper subset prescription number can uniquely identify tuples. Okay, what about the combination of patient number and med code? Can this be reduced and still remain unique? No, this is irreducible, right? Because if we only know the patient number, that doesn't uniquely identify tuples. And if we only know the med code, that doesn't identify tuples. So we have to know both of those, so it is irreducible, so it is a candidate key. If we add dosage to it, though, now this set of 3 attributes is reducible, therefore this is not a candidate key. Patient number, med code, and prescription number, this is actually reducible in 2 different ways, right? We could remove this attribute and it remains unique, Or we could remove these two attributes, and it would still be able to uniquely identify tuples. Okay? So this is unique, but it is not irreducible. And then the same thing for these three stories here, right? As long as we have prescription number, we can uniquely identify all of our tuples. So all of this other stuff is just extra attributes that we could get rid of without impacting our property of uniqueness. Okay, so out of all these, 10 super keys that are all unique, that we can all use to uniquely identify tuples, we have only 2 candidate keys that are unique and irreducible. So in addition, so we've talked super keys, candidate keys, and is that it? Super keys and candidate keys? That's what we've talked about so far. We also have this idea of key and non-key attributes. So each one of our attributes, our atomic attributes in the relation, is always going to be one and only one of these 3 things, either a key attribute, a non-key attribute, or a candidate key. So a key attribute is any attribute that is a proper subset of a candidate key. And again, I'm pointing out here that a set is a subset of itself, but not a proper subset. This is going to be important. A key attribute is a proper subset of a candidate key, and a non-key attribute is any attribute that is not a subset of a candidate key. Okay? So we have these 2 candidate keys, prescription number and then the composite candidate key of patient number and med code. We have 4 atomic attributes in this relation, prescription number, patient number, med code, and dosage. And each one of these 4 attributes is going to be one and only one of these 3 things, either a key attribute, a non-key attribute, or a candidate key. So of those 3 things, what is prescription number? Yeah, it's a candidate key, right? So it is not a proper subset of a candidate key, right? Because there is no proper subset of this, right? And it is not a subset of a candidate key, right? Because it is a subset of a candidate key, right? Therefore, it can't be a non-key attribute, so it's got to be a candidate key. And we've already identified it as a candidate key. What is patient number? Key attribute, non-key attribute, or candidate key? Key attribute, because it is a proper subset of this candidate key. So it's a key attribute. Med code is because it's a proper subset of this candidate key. And then dosage is a non-key attribute because it is not a subset of a candidate key. It's just kind of out there apart from any of our candidate keys. So an attribute is always one and only one of these 3 things. Candidate keys themselves are not key attributes because a set is not a proper subset of itself. Now, primary key, we said, is just a candidate key that we identify as never having a missing value, never being null. And we call this the entity integrity constraint. So the question comes up, when we have more than one candidate key, as we do in this situation, which one should we choose as our primary key? And the technical answer here is that it doesn't matter. Both of these are equally valid to be your primary key. However, there's a little bit of guidance here. One, you want to choose the attribute or combination of attributes that will never, ever be null, right? You might have some situations where you've got a couple of candidate keys that seem fine, but you know that someday down the road, someone's not going to provide their email address. So do you want to force someone to provide the email address or make up an email address for them or just allow them to not have an email address? Well, if you're going to allow them to not have an email address, then you better make sure that you didn't choose email address as your primary key, because we're never going to be able to have a null value for that attribute. Also, choose the one that's easier to deal with, which often is going to be the candidate key that's made up of a fewer number of attributes. In this case, 1 attribute would probably be easier to deal with than 2 attributes or than 12 attributes, right? something that maybe makes some kind of human intelligible sense as being an identifier. Like, I don't know, maybe you can be identified by, I don't know what you can be identified by, some big, long, crazy combination of attributes, or you could be identified by your PeopleSoft ID. Okay, PeopleSoft ID kind of makes sense, right? And then any candidate key not chosen as your primary key are alternate keys, which don't have any real special place in the database. Let's do another one. This looks quite a lot like what we just did, except there are some slight differences in this table or this set of data and what we looked at just a moment ago. I'll point out to you here that prescription number is no longer a unique identifier. We have two different prescription 100s. We have two prescription 102s. So what this is saying to me is that now we've kind of changed our business situation. We've changed our business case. Whereas before we said an individual prescription, you have one prescription that is written for one patient for one medicine. Now what we're saying is that a prescription might have multiple medications written on it. Basically is what this lack of uniqueness here is telling me about the business case. So that's no longer unique. We still have the same situation with patient numbers, that they are not unique. But when combined with the med code, they are unique. So patient number and med code together are unique. And additionally, if you read the story and if you just trust me on how this works out, prescription number and med code are unique when you put them together. So what that tells me also is that when we write a prescription, we can only include a medicine on that prescription one time, right? So I can't write you a prescription to take 3 doses of penicillin and 1 dose of penicillin, right? If I put penicillin on the prescription, it's only on there one time. Okay, so we have these two unique identifiers, patient number and med code, and prescription number and med code. All right, so given this situation, what superkeys do we have? If we start with patient number and med code, that would be a superkey. Patient number, med code, and prescription number together would be a superkey. Prescription or patient number, med code, and dosage together would be a superkey. Prescription number and med code would be a superkey. Prescription number, med code, and dosage would be a superkey. I think we already have prescription number, med code, and patient. Prescription number, med code, yeah, and patient right there. We've already got that, so we don't need to cover that one again. And then all 4 attributes, just as before, prescription number, med code, patient ID, and dosage would be a superkey. So since we have more complex unique identifiers this time, we don't have any that are atomic attributes. We have a smaller number of superkeys. We have just 6 instead of 10, but we have a lot of superkeys here to deal with. So let's identify among these 6 superkeys which ones are candidate keys. And recall, a superkey is unique and a candidate key is unique and irreducible, right? So patient number and med code, can this be reduced and still be unique? No, because if we take away med code, patient number by itself is not unique. And if we take away patient number, med code itself is not unique. So this is unique and irreducible and thus is a candidate key. But if we know patient number and med code, everything else that we add here is just extra, right? So this is reducible because we could get rid of prescription number and it would still be unique. So not a candidate key. We could get rid of dosage and this would still be unique. So that is not a candidate key. Prescription number and med code together, is this a candidate key? Yeah, because we have to have both of these. We cannot reduce this and it remain unique. However, anything that we add to this set of attributes, prescription number, med code, and dosage, we don't need dosage to remain unique. That is reducible. We could get rid of that. So that's not a candidate key. All 4 attributes together are a super key, but it's a super key that is reducible. So this is not a candidate key. So we've identified these 2 candidate keys, prescription number med code and patient number med code. Now we have the 4 atomic attributes that make up the relation: prescription number, patient number, med code, and dosage. And again, they're going to be one and only one of these 3 things, either a candidate key, a key attribute, or a non-key attribute. In this new situation, what of those 3 things is prescription number? Key attribute, non-key attribute, or candidate key? Well, I heard it very quietly out there. Yes, key attribute, because it is a proper subset of this candidate key. Yeah. What about patient number? Key attribute, non-key attribute, or candidate key? Key attribute, because it's a proper subset of a candidate key. Med code? Also a key attribute, because it's a proper subset of both of the candidate keys. That's fine. And then dosage is a non-key attribute. So in fact, we don't have any atomic candidate keys in this relation, right? We just have these 3 attributes that are all 3 proper subsets of one or more of these candidate keys that we have identified. Good stuff. How are we feeling? It's a lot. It's a lot. We're okay. We're going to survive. So this is kind of a handy little chart out of the book. I think it's kind of interesting. So a few things that I'm going to point out here. One, this idea of super key to candidate key to primary key is a stepwise progression, right? So all of our candidate keys are all also super keys. If you're a candidate key, you're always going to be a super key, but the reverse is not true. Not all super keys are candidate keys, right? We're getting more and more restrictive with our rules. So we go from unique to unique and irreducible, and then it's not shown here, but with the primary key, we're unique, irreducible, and not null. Unique, irreducible, and not null, which we call the entity integrity constraint. Not null, no missing values for our primary keys. So far with these key constraints, our super keys, candidate keys, and primary keys, we're talking about individual the screen goes yellow so gradually that I don't notice until I'm like, oh, this looks nasty. Now it's like, ooh, wake up. So what we've talked about so far is talking about individual entities or individual relations in our database, okay? So now with our referential integrity constraint, we're talking about constraints between 2 relations within our database, right? So this maintains consistency across the data, across the tuples in these 2 relations. And so the basic idea of referential integrity says that when a tuple in one relation refers to a tuple in another relation, it must be referring to a tuple that exists. Kind of makes sense. If a tuple refers to another tuple, it has to refer to something that exists. It can't refer to something that's not there. That is the referential integrity constraint. And then a special form, or kind of the operationalization of the referential integrity constraint. What really makes the referential integrity constraint works is the foreign key constraint. So our foreign key constraint, and I told you we would put some actual definitions to these words. Our foreign key constraint is what creates this relationship between relations in our database, okay? And we say a foreign key is some attribute or set of attributes, some attribute in a relation that shares the same domain with a candidate key in another relation. Okay, a foreign key is an attribute or set of attributes in a relation that shares the same domain of values with a candidate key in some other relation. And so we say that foreign key references the relation the other relation, right? And so we refer to this as inclusion dependency. Okay, and we write this in our relational algebra notation like this. We say attribute 2 in relation to is inclusion dependent on the set of values for attribute 1 in relation 1. Okay, this is saying all the values of our foreign key must be found in the domain of values of the candidate key to which it refers. Okay, it has to be a candidate key. Preferably, this is going to be your primary key in the relation that you are referring to. That's typically going to make the most sense. So in order to establish a relationship between two relations, we create a foreign key in one of the relations that's going to refer to a tuple in another relation. And so all the values of our foreign key must be in the domain of values of the candidate key to which it's referring. Let's put some data to this to make it make a little bit more sense. So hopefully we're all kind of familiar with this idea of plants undertake 0 to many projects, and a project is undertaken by exactly one plant, right? Our Bearcat story over and over again. In this relationship, this one-to-many relationship, who would we say is the parent in this relationship, the plant or the project? Plant is the parent, right? A plant has many projects. A project has just one plant. So our foreign key is going to go with the child in this parent-child relationship, in this case, project. Okay? And we kind of had a little foreshadowing of this example a couple of classes ago, where we have our plant relation that has these 1, 2, 3 attributes describing Black Horse, Maid Creek, Whitefield, River Oaks, Kings Island, and Ashton. And then we have this project relation that describes our 7 projects. And each project has a value for this project, plant number attribute. So this attribute is a foreign key that refers to this candidate key, and in fact, the primary key of this plant relation. This is a foreign key referring to this candidate key. So this is establishing our foreign key constraint and ultimately our referential integrity constraint. And recall, our foreign key constraint says that all values of our foreign key must be in the domain of values of the candidate key to which it refers. Okay, well, let's see if that's correct. So our solar heating project is in plant 11, right? So that is in the domain of values of plant number in this relation that we're referring to. Same with robot sweeping. 11 is in this domain of values. 17 is in this domain of values. 12 is in this domain of values. And 19 is in this domain of values. So all values of our foreign key must be in the domain of values of the candidate key to which it refers. We can't assign a project to plant number 25 because there is no plant number 25. That's not in the domain of values of the candidate key that we're referring to. And if we did have a project assigned to plant 25, then that tuple would be attempting to refer to a tuple that doesn't exist in this other relationship, which is a violation of our referential integrity constraint that says a tuple has to refer to another tuple that exists. So that's how the foreign key constraint kind of enforces our referential integrity constraint. It's fine that we have some plants that don't have any projects. Has optional participation here. But all of our projects have to be assigned to a plant that exists. So when we get to writing our DDL code, and we'll actually be doing this next week in class, we're going to see the syntax for how when we define this attribute, that we link it to this attribute in this other relation using our foreign key constraint. And then when you start trying to put values in here, if that value doesn't exist in the domain of values of the candidate key to which it's referring, the database is going to give you an error message and simply will not allow it to happen. All right, we're getting to it now. Feeling good. Thoughts, questions, comments, concerns?
So,
Yeah.
when a primary key in one table is being referenced in another table, that becomes a foreign key in that table. Is that right?
Yeah, when a primary key is being referred to, this it's a foreign key in this table that is doing the referring. Yeah. Yep. And it doesn't have to be the primary key. It just has to be a candidate key, but 99% of the time it's going to be the primary key. It just kind of makes the most sense. All right, so I mentioned that our foreign key is going to go in the child entity in our parent-child relationship. So we already went through this. Oh, this is employees and plants. Okay, all right. So in this case, plant is the parent, employee is the child, because the plant has many employees, and employee has just one plant. And so we put the foreign key in the child entity, in this case, employees. So this is modeled correctly, right? Plant number here is a foreign key that is referring to this plant number attribute. So employee, Adam is at plant 10. This employee is at plant 10, plant 11, plant 11. Okay, this makes total sense. But what if we messed this up and we put the foreign key with the parent, right? Instead of putting it with the child. So we're going to put the employee ID with the plant instead of the plant ID with the employee. So we're still able to link all this together, but now see that we've had to duplicate all of the data for the plant's name and the plant budget for every employee that is assigned to work at that plant. Okay, so we're still able to get this mapping of employees to plants. However, what have we introduced here now? What's the problem? Yeah, we've introduced redundancy, right? So now we don't have plant 10 is Underwood just one time, and plant 11 is Garnett just one time. We have to have Underwood 3 times, once for each employee, and Garnett twice, once for each employee. So introduce redundant data. This is a bad use of data storage. This is just going to create an endless number of problems if we do this backwards, putting the foreign key with the parent instead of with the child. Yeah, so this is the correct, this is the incorrect. Now, there's the question of what about when we have a one-to-one relationship where there is no clear parent or child, right? So we have this situation where we have faculty that are the head of departments. So faculty is head of a minimum of 0 and a maximum of 1 departments. A department always has exactly 1 faculty member. So in this situation, we want to put the foreign key with the relation that has mandatory participation in the relationship, right? Because every department is going to have a value for department head, right? Because it has mandatory participation. However, not every faculty member is going to have a value for the department they are a head of, because they have optional participation, right? So this is the right way. If we did this the other way, if we put the foreign key over here with faculty, this actually still works okay. We don't introduce a lot of data redundancy, but what have we introduced that makes our data a little more difficult to work with? Yeah, a bunch of null values, right? And as we will come to see when we start writing SQL code and doing some things like that, null values just make SQL act weird sometimes. Like it's the more you can avoid having a lot of null values, the better off you're going to be. So no redundancy here, but this is just a less effective way to model this. And then finally, there's this weird case that you could have a one-to-one relationship where instead of having optional and mandatory, you might have mandatory participation of both entities. And I can't think of a lot of real good examples of where you would have a one-to-one relationship with mandatory participation, that it wouldn't make as much, if not more sense, for those two entities just to be in one table together. But it's not going to matter at all where you put the foreign key in such a situation. Or you could have kind of the other extreme, a one-to-one relationship where both sides have optional participation. And there's not going to be a hard and fast rule here either, except that you're probably going to be better off putting the foreign key in the entity that has fewer instances, because you're just going to naturally wind up with fewer null values that way. Now, one way to solve the problem of having any null values would be to use a gerund to decompose that relationship, and then we would have no null values at all, because every relationship would just be a row in our gerund. We'll have some examples in coming classes that kind of make that a little bit more clear if it's not. Foreign key placement, another very important thing. And of course, we had situations like in the Bearcat story, where we can have multiple relationships between two entities, right? We have this situation where we have the one-to-one relationship of faculty being head of departments, and then a one-to-many relationship where faculty are members of departments, right? So we can have a foreign key in the faculty table that's establishing this member of relationship, right? So this is describing what department each faculty member is a member of. But then in departments, we have a foreign key that's referring back to the faculty table, describing which faculty member is the head of that department. Okay, so in this case, we have a foreign key. We have two relationships between these two tables, and we have a foreign key in both sides, or in both tables, you know, depending on which relationship we're talking about. Good stuff. And of course, this faculty table could have any number of foreign keys, right? If faculty are in relationships with courses, right? Well, that would not be a great example because of faculty. If faculty are in a relationship with offices, right? They might have a foreign key that links them to their office. Something like that. So you can have, there's going to be a foreign key for every relationship that an entity is in. Yeah, details about what I just said. Oh, and then here's just the example of what happens if we were to do it the wrong way and put the foreign key for this member of relationship in departments. We're going to get all this redundant data and kind of nonsense like we've seen in a couple of examples before. All right, so superkeys, candidate keys, key attributes, non-key attributes, primary keys, and alternate keys. Superkeys are one thing, which is unique. Candidate keys are unique and irreducible. Primary keys are unique, irreducible, and cannot be null, or the entity integrity constraint. Key attributes are proper subsets of a candidate key. And non-key attributes are not a subset of a candidate key, right? Not a subset of a candidate key, because a candidate key is a subset of itself. That's why it has to be not a subset of a candidate key. Otherwise, a candidate key would be a non-key attribute. And then alternate keys are just candidate keys that we did not select as the primary key. The entity integrity constraint says that if a tuple refers to a tuple in another relation, it has to refer to a tuple that, entity integrity constraint is the null, can't be null. Referential integrity constraint says if a tuple in one relation refers to a tuple in some other relation, it has to refer to a tuple that exists, and that is kind of operationalized or enforced by the foreign key constraint, which says all values of a foreign key must be in the domain of values of the candidate key to which it refers, right? That foreign key constraint is what actually makes the referential integrity constraint like be, right? because we can't have a value of a foreign key that's not in the domain of values of the candidate key that we're referring to. Otherwise, we would be trying to refer to a tuple that doesn't exist, violating our referential integrity constraint. Whew, it's a lot of words. We can do one more module, 6.4. Let's roll, let's do it. We're going to talk just a little bit about relational algebra. And we're actually just kind of getting introduced to this idea now. We're going to talk more about relational algebra after exam 1. So we're going to talk briefly about our 8 relational algebra operations. We're going to talk about 2 unary operators, select and project, and then about our 3 set theory operators, union, intersection, and difference, which we already talked about a little bit earlier. And then we're going to very briefly look at the natural join. So relational algebra basically just lets us kind of abstractly talk about relations and relationships without getting hung up on what the actual attributes and values are, right? Just like regular algebra lets us talk about numbers without using numbers, right? So, you know, a simple algebraic equation would be to say the area of this room is the length times the width, right? And we can operationalize this. We can use this formula to calculate the area of any room or any two-dimensional space, right? And we can plug in some values here and say, okay, well, if the length is 10 and the width is 20, so area equals length times width, area equals 10 times 20, so our area would be 200, right? And further, we can nest these algebraic operations to come up with kind of other things, right? So if we wanted a room that had 4 times the area of this, we could express that as 4a, which is 4L times W, which would be, in this case, 10 times 20, 200, so 800 would be 4 times the size of this 200 square foot room, right? So this is our kind of grade school algebra. Our relational algebra just kind of does the same thing, right? Instead of saying we have a relation students that's made up of PeopleSoft ID, first name, last name, email address, and all that stuff, we say we have a relation that has these attributes, A sub 1, A sub 2, A sub 3, and we can kind of see what select and project and set theory operators and joins would do without getting caught up about what we're actually talking about. So we're going to say a relation that we could just generically call R is made up of attributes, and we'll call them like A sub 1, A sub 2, A sub 3, up to however many attributes we have, A sub n. So we would say our relation schema in this case is R, and then in parentheses, this list of attributes, right? This is just like saying students, PeopleSoft ID, first name, last name, email address, whatever, except we don't care what we're actually talking about here. We've abstracted that away. So that's our relation. These attributes we define as an ordered set in D, where n is the name of the attribute and D is the domain of values for the attribute. And we can represent all of the attributes in our relation as this vector C. Okay, so C is a vector that is made up of these ordered sets in D for each attribute that is in our relation. So our relation is a set RC, where C is this vector of attributes, where R is the name of the relation schema, and C is the list of attributes making up the relation. So our database is made up of multiple relations, RC, which is equivalent to the relation and all the attributes, or the relation and all the names and domains of all the attributes that are in that relation, okay? This is a lot of very convoluted stuff just to say, hey, we're going to call our relations R and our attributes A1, A2, A3, A4, A5, and not really care about what they're actually representing at this point in time. So we're going to come back to this in a couple of classes, but just to kind of give you a little sneak peek, that's how we're going to be thinking about relations and attributes. And then here are the operations that we can perform on these relations and attributes. So we're first going to talk about these two unary operators, unary meaning that they are executed only on a single relation, project and select, and then our binary operators, meaning that they are executed on exactly two relations. So our two unary operators, selection and projection. We have some Greek symbols here. This is the lowercase sigma representing select, lowercase pi representing project. And then our 6 binary operators, union, intersection, and difference. These 3 are set theory operators. This looks a lot like a U, but is actually kind of a stretched out U. This is the upside down version of this. Difference is just a minus sign. And then join, Cartesian product, and difference. We'll talk about these two, I think, after the exam. Join is this X with the little bars on the end. Kind of looks like a bow tie to me. So imagine we have these 3 plants, AW plant, Texas plant, and projects. So these are award-winning plants. These are plants that are in Texas, and projects we'll talk about in just a minute. So select is going to return a horizontal set of rows, or tuples, right? So selection returns a subset of tuples. Projection returns a subset of attributes, okay? So subset of tuples that match some criteria. Projection is a subset of attributes that we are interested in seeing the values of. That's what I just said. Select returns a horizontal subset of tuples that satisfy a selection condition from the relation. So we're going to write our relational algebra statement like this. Our lowercase sigma, the Boolean selection criteria, and then the relation that we are executing this selection on. So Boolean expression meaning one that's going to evaluate to either true or false for every tuple in the relation. So in this case, let's imagine we wanted to find all of our award-winning plants, so this is the relation that we're dealing with, that have a budget that is greater than 2 million. So this is a Boolean expression where we're looking for the value of AW plant budget, and we're comparing the value of this attribute to 2 million, and it's going to evaluate to either true or false. Okay, and if it evaluates to true, it would be returned by the selection, and if it's false, it will not be. And this is what the SQL statement that goes along with this relational algebra would look like. We're going to select all attributes from this relation AW plant where this condition, this Boolean expression, evaluates to true. Okay, so we look at this value in each tuple. Is 2,500,000 greater than 2 million? Yes, so that's going to evaluate to true, and this tuple will be returned in the new relation that's created. Is 1,930,000 greater than 2 million? No, so that evaluates to false, so that would not return. 200 or 2.9 million, yes, that would return. No, yes, yes. So all of these tuples that evaluate to true are returned, and a new relation is created in memory on the database server. So this is the data that is stored like on the hard drive of the database server. When we run this SQL query that corresponds to this relational algebra expression, this new relation, which has a reduced cardinality, is going to be created and stored in memory for as long as we are interacting with it. When we're done with it, the server is going to release the memory, and if we wanted to generate this again, we would have to run the SQL statement again, right? But note that here we have 1, 2, 3, 4, 5, 6 tuples, so this relation has a cardinality of 6. This selection, by returning only tuples where this criteria evaluates to true, has created a relation with a reduced cardinality. So by doing this, now it's going to be more computationally efficient to join this relation to some other relation because there's going to be fewer operations that have to take place. Project, on the other hand, returns a vertical subset of attributes that we are interested in seeing. Okay, so we use the lowercase pi. Here we're going to have the name of the relation, and here just a comma delimited list of the attributes that we are interested in seeing. Okay? So if we wanted to see just the plant number and budget for each of our award-winning plants, we don't care about the name of the plant, all we want is the number and the budget, we would project from AW plant these attributes, AW plant number and AW plant budget, and the SQL that goes along with this would look like this. Select, and here's our comma delimited list of attributes, AW plant number and AW plant budget, from this table or relation AW plant. So even though it's project, it's still right here after the select, right? So it's select, and then here are the attributes we're projecting from AW plant. And so now we have the same cardinality. We didn't reduce the number of tuples or rows, but we do have a reduced degree. Our degree went from 1, 2, 3 down to just 2. Okay? So we still simplified this relation that results. And then, I thought I had another example here. Of course, we can also nest these things together so we can simultaneously select and project, thus reducing both the cardinality and the degree of the resulting relation. I think the example may be forthcoming on that. But if not, know that there will be an example someday, and I just foreshadowed it. So those are our two unary operators. And now to kind of quickly look at a couple of binary operators, we're going to talk first about our set theory operators and then a little bit about the natural join. Okay, so in order to use any of our set operators, the two sets of data have to be what we call union compatible. Okay, and this is true for union, intersection, and difference, right? It's, I think, just kind of coincidence that this is called union and we talk about union compatibility. But union compatibility means that the two relations have the same degree or the same number of attributes, and that the pairs of attributes from the two relations have the same domain. Okay, so they have to basically be similar looking data sets, right? So if you were getting the union of, students at two different universities, the data sets would need to both be, student ID, first name, last name, phone number, something like that. You couldn't have two very different data sets and do any of these set operators. So same degree, and the attributes are in the same domain. So if we wanted to see, so we have our award-winning plants and our Texas plants. These two relations are union compatible because they both have 1, 2, 3 attributes, and the attributes are in the same domain. The first attribute is describing the plant number, the second attribute is describing the name of the plant, and the third attribute is describing the budget of the plant, right? If this was not the budget of the plant, but it was the telephone number of the plant, then these two things would not be union compatible. None of this would make sense to do. Okay, so for our union compatibility, here's our relational algebra symbol for union. So we're taking the union of AW plant and TX plant, okay? And this is essentially giving us all of the plants that are in AW plant or Texas plant. And this is how we would write that. We have basically two complete SQL statements, select asterisk from AW plant, and select asterisk from Texas plant, and we just put the word union in between them. And when we do that, we have these two source relations, and we have this relation as a result. So if we have, let's say, 1, 2, 3, 4, 5, 6 award-winning plants and 1, 2, 3 Texas plants, how many plants, or what do we expect the cardinality of AW plant to be? 6 and 3, 9? 2, 3, 4, 5, 6, 7, 8. Why is it 8 instead of 9? Yeah, there's some repetition, right? So we have these two data sets of, what is it, award-winning and Texas, right? So we've got Black Horse is, what am I doing? not H. Black Horse is plant 11, Maid Creek is 13, Whitefield is 12, River Oaks is 17, Kings Island is 19, Ashton is 15, and then in Texas plants, we have Southern Oaks is 16, River Oaks is 17, and Kingwood is 18, right? So we have one plant, number 17, River Oaks, that is a Texas plant and an award-winning plant. So the point is, when we do this union, any tuples or any data points that are in both data sets aren't going to be repeated here. They still just show up once, right? Because they can't show up multiple times, because then we would have two identical tuples, and we can't have identical tuples in a relation. The intersection, this is kind of the equivalent of saying and. What plants are in Texas and are award-winning plants? Same format as our union. We have two SQL statements, select asterisk from AW plant, select asterisk from Texas plant, put the word intersect between them, and we're going to get only this one plant, number 17, River Oaks, which happens to be in both data sets. And then our difference is equivalent to saying not. And we can do this in either direction. Which plants are in Texas but are not award-winning? Well, that's Texas plants minus award-winning plants. So Southern Oaks, River Oaks, and Kingwood, so those are our Texas plants, minus what's in award-winning plants. Well, that's going to take out River Oaks, and we're going to wind up with just Southern Oaks and Kingwood. Or in the other direction, what plants are award-winning, but not in Texas? And so that's going to get rid of this River Oaks plant, which is the only award-winning plant that is in Texas, right? So we're taking out Texas plants from award-winning. So that's the basic idea of our set operators. And then I believe the final thing that we are talking about tonight, oh, and good thing too, is the natural join. And we're going to talk a lot about different types of joins as we get further into class. But the natural join is going to combine two relations to create a third relation in memory that contains values that come from the set of attributes in both of the relations. So when we have this foreign key relationship establishing the relationship between projects and plants, we can say something like select asterisk from AW plant, natural join, Texas plant, and there are some rules about how the attributes have to be named for a natural join. Or we could similarly do select asterisk from AW plant, inner join, Texas plant on this Boolean condition where the value for the foreign key is equal to the value of the candidate key that it refers to. And this is going to create a new relation that has, since we're projecting all of the attributes, a degree that is equal to the degree of relation 1 plus the degree of relation 2. So since we have 3 attributes here and 3 attributes here, we'll have 6 attributes in this resulting relation, and a cardinality that is equal to the number of times that we have a matching value of the foreign key and the candidate key that it is referring to, right? Because if we had optional participation on both sides, we could have some situations where we have projects that are not assigned to plants or plants that don't have any projects, right? So this is how many times that we do have that condition of equality met. So we'll be doing joins a lot as we start writing our SQL code. And that's it. That's it for 6.4, and that's it for the night. So the 8 operations in relational algebra, we talked about select, project, which are 2 unary operators, union, intersection, difference, Cartesian product, division, and join. Select and project. Select returns a subset of what? Tuples that match some Boolean condition. And project returns a subset of attributes that we are interested in. Union is basically you're in either data set, it's or, intersection is and difference is not. And then natural join returns a relation that is a combination of attributes from the two relations that are being joined together based on some equality of the foreign key value and the candidate key that it is referring to. All right, guys, thoughts, comments, concerns, questions? If you just want to throw things at me, that's okay too. I don't know how you guys on Zoom are going to do that, but you can throw emails at me, I guess. All right, well, if there's nothing else, you guys have a safe night. Get home safely. Have a great rest of your week. Do some great things, and we'll see you next week.